All right. Yeah, thank you very much. Thank you for having me. I'm happy to be here today. And yeah, the title is very general, as Simon already mentioned. I wanted to make it more descriptive than impressive, I guess. But the idea is that I would like to cover a bit the last year's development in representation learning of audio. And also I will mention generation, but this is not really the main focus of this talk. I hope I can give you some insights simply by looking back a bit and looking at the trends. At the same time, I will actually base most of the talk and the examples on our work at Sony CSL because we obviously follow trends anyway. So I think this is then actually a good proxy. So yeah, I'm Stefan Lattner, research leader of Sony CSL. Very quickly, what is Sony CSL? Sony Computer Science Laboratories. There are different locations in Tokyo, Paris, Kyoto, and Rome, and actually we are fundamental research labs. And there are all kinds of different research areas where many people are working on, but in Paris we have the music team, and our mission is to explore new and innovative ways to apply artificial intelligence in music production. And this is our team, and I also wanted to show this picture because a lot of works that I'm mentioning today is basically done by those people, not by me only. And so they're very talented, motivated people, and yeah, great, thank you for their work. So the right part here that you see is research, so we have mainly research. But there's also a bit of development that we do because we need to put, or we want to put our developments and technologies in actually plugins, stuff that actually works for music producers to be able to then test them, get some feedback, maybe improve on that and so on. We're also working with other Sony departments and with artists and to some degree with external companies. And over the years, we created a nice palette of AI tools for music production. So there are AI companions, like more these programs or technology that creates a more temporal, it generates music material that is more extended in time. So like DrumNet was creating rhythms, or Differiff is now a new prototype that basically is a stamp generator. Then we have neural audio synthesizers like GAN is very well known, I guess. And so other that create short samples of audio. And we have audio processing mastering tools, writing assistants, and audio analysis tools. So what I will talk about today is basically I want to mention some ideas about low-level representations and also low-level representation learning, because I think this is still a bit underrated topic, or let's say one can do a lot already in terms of invariance learning in low-level representations, and we don't need huge models to basically learn some invariances like transposition invariance or time shift invariance, or also tempo invariance. Then I will mention high-level representations. Basically, the trend is self-supervised learning, obviously, and there were over time different self-supervised learning paradigms. So we had contrastive learning, then batch statistic-based learning, and then we went into predictive CMS networks where we have asymmetry between the encoders of the data encoders that are usually symmetric. And recently there were some works in equivariance constraint, also to use equivariant constraints for learning of interesting representations or outputs. And I will also mention an audio codec that we developed, or actually Marco developed. He should be here at one point, but not yet, I guess. So Marco Passini developed this music to latent audio codec. Audio codec. I will mention this as well because I think it's a very interesting work. And it's also obviously high-level representations. And yeah, and then I will quickly go into musical audio synthesis, synthesis with GANs. It's really an old work, but it, you know, it covers the whole transition into latent diffusion and autoregressive generation. And for autoregressive generation, there's an interesting new trend coming up, I hope. Let's see where this leads us to. But yeah, I will mention this as well. It's continuous autoregressive generation, so without the need to discretize your data. Okay, in terms of low-level representations, what interests me are these wavelet scattering transform-like transformations, because here you can get, as I said already, interesting invariances, and also basically a good summary of what you're looking at in audio in terms of second order representation learning, and also it was a bit of a topic of debate which representations we should use for audio synthesis, and we did some work on that, and I think I found my favorite representation for audio synthesis. It's an interesting system, by the way. It already broke my computer, and now it's also doing a little bit weird. So yeah, exactly. I have my favorite, but still it's interesting that it's often still raw audio is used for learning autoencoders, for example. I think actually this is a bit of a waste of computation, but yeah, we will see. Okay, let's start very low level. So you all know this idea, if we have a phase-shifted sine wave, we can basically define two filters, which is the sine and the cosine filter. And if we then project this filter responses in a complex valued space, this is like in a discrete signal, this would be just a dot product. And then we obtain these filter responses that you see to the left. And they uniquely define basically the phase-shifted sine wave. So we basically can use two fixed phase-shifted waves, like sine and cosine, in order to describe such a signal. And what we see already here is that we get a specific invariance, which is the arrow that is basically defining the point in the complex valued space does not change when we perform this phase shift. So basically we get the magnitude of this signal in the complex valued space is fixed. So in this unit circle it would stay 1. And that's an interesting property. I mean, we can also do reconstruction using this. So we can just perform the inverse and we get the phase shifted sine wave again if we have these filters that are tuned in frequency to the sine wave. And then we obtain, of course, everyone knows it, our STFT spectrogram. Let's see if we can hear it. No, we can't. But yeah, maybe you could solve it while it's not so important. It's just an ancient example. But what we see is, as we get these invariances to phase shift, we get a very clean signal on the left, and the phase would be extremely chaotic, and often we throw this away when it comes to analysis, audio analysis. And what is interesting is that we can do this in a second order transform, so we can also perform such an analysis, a filtering of complex valued wavelets in that example, and they are localized, so they're only very local. And if we filter this signal, like basically performing a convolution, we then basically measure distances in this image. So the interesting part is, I mean, here we get transposition equivariance or translation equivariance, which means that the resulting magnitude spectrogram would just shift when we shift, if we shift the signal, or in this case the image. Yeah. But as we saw before, to some degree, we also get some invariance. So the magnitudes are locally invariant. So if we shift only a little bit, there won't be a big change in our filter responses. But this has some limitations. For example, it's not fully translation invariant, or in this case transposition invariant. So if we shift too far, the CQT spectrogram on the left, up and down, we would get actually a different signal in our output. And it's also overcomplete, which means that if you define all kinds of different frequencies of wavelets, a lot of them are actually useless for our data because there are some characteristic distances in the data, and a lot of frequencies are just not in there. So the idea was in a previous work, can't we just learn such filters? Exactly. Can't we just learn such filters? And maybe also defining these filters that they span the whole frequency range. Because if they span the whole frequency range and we just convolve CQT spectrograms that you see here on the left, if we convolve them only in time, what we get is actually full transposition invariance. Because basically we get again a two-dimensional spectrogram because we don't convolve in the frequency dimension, and this has very interesting properties. So first, because we have also a 2D transform, we measure also distances in time, and of course we measure intervals in our data, and this can lead to very good representations that we can use for audio alignment, for example. So here's an example of a similar model that was also fully transposition invariant. I chose this example because it's very clear with the symbols on top. If we have transposed versions, transposed segments in the data, and we perform a self-similarity matrix in this representation space, we actually get these nice diagonals. And we can use those diagonals to basically do repeated section discovery. And also alignment, of course. So for example, in audio to score alignment, the technique that is used is that you render a MIDI file into audio and then you perform an alignment between two audio files and using dynamic time warping. And we showed in this paper that you can actually improved on the state of the art for audio to score alignment. We also get some tempo invariance, and critically we get transposition invariance. So if you see, these features perform better than chroma features for audio alignment, but at the same time, chroma features are not transposition invariant at all. So we didn't test for transposition invariance here, but we can do this. So this would be interesting for cover song detection, for example, or if we have a phase pitch drift in a cappella, or simply for structure analysis. And I mean this paper didn't get a lot of attention, even though it got the best paper award, but we didn't follow up on that because we just worked on something else, and somehow no one found it because probably also we didn't put the tasks in the title. So audio to score alignment and repeated section discovery, we had actually very good results. So I wanted to invite you to look at this again, maybe. I mean, you can even have very explicit tempo invariance if you do a third order transform. If you're interested, let's talk about it later. And and if we do this on one-dimensional signals, we get these nice gamma tone filters, or gamma tone-like filters. Gabor filters. And if we can also do this on phase, on rotated MNIST digits, and we get rotation invariance. Why I show you this is that if we perform a PCA on the magnitude and the phase difference space of such rotated MNIST digits, we get on the left side, in the magnitude space, we get the identity of those digits invariant to rotation. And on the right side, we get the rotation angles, very nicely clustered as well, or in this manifold at least. And this could be also very interesting for audio analysis, because if we do audio alignment or we want to really do structure analysis, we can not only detect similar or the same segments that are transposed, mutually transposed, but we can also identify how they are transposed. So yeah, that's why I think it's a very interesting representation. And the code is online. I checked yesterday that it works with modern Python versions as well, because it's already work from 2019, I guess. Yeah. So yeah, that's it for the first paper. And then, as I said, there was this discussion, and I don't know, the jury is still out, what's the best low-level representation for audio generation, at least for things if we want to do invertible representation learning, like autoencoders, so it's also relevant. And we did this study 2019 as well already, where we compared a lot of different low-level representations for generation. And we used a GAN. So one could now say, okay, a GAN was very different than modern models, but I think a GAN was very sensitive in training. So basically, we have a very pessimistic evaluation on which of these representations are stable or nice to learn. Some of them are not really invertible naturally, so we need some form of approximation or optimization. So that's why they are anyway not the most optimal ones. But yeah, what we did is we trained the GAN on ancient data. Do we have sound right now? Yeah. I think most of you know ancient. And if we then try to generate in the waveform or learn on the waveform domain and generate sounds again. We have, okay, that's close to to this fart gun that we're always talking about. But yeah, you see, especially high frequencies are not represented very nicely. Generally, we get very noisy signals. And that's actually pretty obvious if I will tell you soon. So what GANs used when they first did a generation of one-shot sounds, GANsynth was one of the first GAN models that actually made it work, that you could actually generate these nsynth sounds. They used magnitude and instantaneous frequency. The advantage here is that it's somehow invertible, and you get a pretty clean phase spectrogram because, do we see this here? Yeah. Because what you actually do is in every frequency bin, you calculate the phase difference between all the different frames, and the phase difference is much more clean if you have a static signal. If you see this here on the right side, wherever you have a high magnitude, you also get a pretty clean phase spectrogram. Yeah, and so generally this looks very nice, and it's good to learn for a generative model. But the problem is that you actually by only taking the differences, the phase differences over time, individually for every bin, you lose all the correlations of phases between the frequencies. So it sounded quite good for ancient data, but what you lose is actually steep transients, and because you need some phase alignment if you want to have steep transients. So if you just randomize the phase of any audio, and this is actually what results from it, then you actually get a very weak reconstruction. So what we also tried is complex valued SDFD. actually been surprised to some degree. Huh? Okay, let's. Yeah. It actually worked quite well. So complex valued SDFT, we don't compute the magnitude and phase, we just take the complex valued components directly. And we also could, with objective metrics, show that complex and MAG-EF actually perform pretty well in terms of FAD. For example, here for the conditional case, complex actually outperformed all the other representations. And that's actually, if you think about it, pretty obvious, because I mean, we know already what the best filters are for low-level audio representations. I mean, we perform SDFT because of a reason. We know that we have filters that are tuned to all frequencies that could be in the signal. And of course, if we replace the first layer of a model with just sine and cosine filters, we make the job much easier for the model to learn. And it's invertible, so why not use this for all representations? And actually, that's my conviction that it doesn't make much sense to train a model on the signal domain directly for any task. We should just use complex valued SDFTs, especially when it comes to models where we need reconstruction. Yeah. Then let's go to higher level representation learning. I don't know what's the time. Looks good. Higher level representation learning. Okay, I mentioned it already. It's about self-supervised learning mainly, and about the trends in self-supervised learning. And I also will mention the music to latent audio codec. I wanted to include sample match. This is one of the most simple contrastive learning approaches that we did 2 years ago in Izmir conference. And we now have a web application online that is free to use without registration, which could be interesting for those of you that are music producers as well. And how it works is basically you upload your mix of audio, and the model will sort a library of one-shot drum samples according to what it thinks that fit best to your mix. And that's very useful, because if you want to find a snare that fits your mix in a big library, that's a pretty tedious process. And so yeah, we basically combined already. We generated a big library with DrumNet, and then put this into this web application, so you can basically retrieve DrumNet one-shot samples based on your input mix. So you can check it's on Sony Tech Hub, or you can check the QR code. And this worked in a very simple way. Simple contrastive learning. We had our mix encoder and the sample encoder, and we knew which samples came from which mix. And so we could just simply train such a geometric space where we try to bring the embeddings of samples and mixes that we know that fit together close in space, and we push away all the other samples. And that's generally a very stable way to train a self-supervised learning space. But with contrastive learning, in general, you have specific problems. First, you get some false negatives, because there could be samples that fit your mix, but they just didn't happen to be included in your mix, in your data set. So you also push away samples that actually would fit your mix very well. And also it's batch size dependent. So because you always push away only negatives in your batch. So that's also a bit of a problem. And you never have enough negatives. I think Jan Luc once said this for contrastive learning. There could always be negatives that just are positioned close to your data at inference time, even though you don't want it, but you just didn't show the model these negatives during training. There are several weaknesses in the basic form of contrastive learning. What we did, like with Bernardo Torres, work where we tried to learn a singer identity space. And so you see that similar singers or the same singers should be clustered in space close superclasses in space. And yeah, what we did is just we took the recording of a single singer, and we take 2 segments, random segments of this recording, and we know this is the same singer, so we bring it close in space. And so we had this very general pipeline, and we tried different self-supervised learning methods or paradigms for this task. So we had batch size dependent and batch size independent contrastive learning. So in contrast, self-supervised learning. So contrastive learning, we know we have specific weaknesses. It's batch size dependent, but also it uses negatives. Then we had developments where people tried to eliminate negatives. So this was the uniformity alignment, and VIGREG was 2 examples of this, where, I mean, the idea is always we try not to collapse the space. We bring stuff together, but if we bring everything together that we know that fits, the space just collapses. And so there are different ways to try to basically not make the space collapse. For example, uniformity alignment is such a method where you try to equally position all your data in a hypersphere. And VIGREG was a statistic-based metric or constraint where you try to constrain your latent space to be of unit variance, and you diagonalize your covariance matrix, meaning you want the dimensions to be independent of each other. And this also prevents collapse, obviously, because if you have your uniform variance, that's obviously not a collapse. And this also worked to some degree. It was actually very interesting. But at the same time, 2020, this all happened around 2020. Then BIOL came up, bootstrap your own latents. And this was a pretty interesting approach where we actually used, because all of them are using CMA's networks, 2 encoders, and we bring then the embeddings close in space. And BIOL basically broke this symmetry, and we said, okay, let's have an encoder and another encoder that is basically exponential moving average of the parameters during training of the initial encoder. So we basically have a delayed version of the encoder that we're training. And we predict latent representations of this delayed version from the latent representations of the original version. So that's a scheme of BIOL. Basically, the bottom is the delayed version, and yeah, and if you predict the latence of the delayed encoder from the latence of the encoder that we learn, and we of course have to perform here a stop gradient operation, then we eliminate not only negatives, but we also become invariant to batch size. And that's a very important step actually, and this also made it work better than the other methods, and we could identify this in this work of singer identity representation learning, that BIOL worked actually best for most of our downstream tasks. So a very pretty new method now, because if you look at BIOL, you always have to input 2 different views of your data. That's very common in self-supervised learning. You input the original data point, and then you input the augmented version where you change your data. Let's say for images, you change the brightness or color or anything you want to become invariant to. Basically, whatever you augment the data with, the representations will become invariant too, which is generally a nice thing because it allows you to control what you want to be invariant. But also it needs some human input or some domain knowledge still, which is to some degree could be argued also limiting. And so now there are these JEPA, joint embedding predictive architecture approaches, where you do something very similar like in BIOL, but you not predicting one vector from one data point, but you basically take a grid of your data and you predict and you mask out some of your patches, like image patches, and then you predict patches, the masked out patches from those that are not masked out in the latent space. So really in the latent representations, you predict some patches from the other patches. And this doesn't need augmentation, which is very useful, of course, because then it's a very general method. You can do this as well for audio spectrograms. In this work, we actually wanted to tackle a bit of a different problem. We wanted to learn which stems fit to which mix, so stem compatibility estimation. And in this task, we actually didn't need to mask out some patches because we actually just wanted to align stems that fit a specific mix, and we want to learn how which stems fit which mix. So we actually have anyway different latents in our context, in our target, and we then predict the target representations from the context representations. And the advantage here is that we also get some time alignment. In the case where we predict only one, like in CHEPA, like in BIOL, where we predict only one latent, or also in CLAP, for example, you have 10 seconds as your input, like this joint embedding space of text and audio, CLAP. You always predict one latent from your 10-second input, one latent vector, and here we have a set of latent vectors that are also span time and frequency. And for some tasks, this can be interesting. For example, if you want to do alignment also between stems and mixes, what we wanted to do. So first, just to show that the model learned some music theory, we did some analysis of our latent space and cluster analysis, where we showed, or where we evaluated if segments of a specific chord fit to the scale of the segment. So that basically, can the model learn which chords fit to which scale? So for example, if you have D as a key, we find that the D major chord so patches of the D major chord are close in space, but also G are close and patches of A. So these are the main chords of the D major key, for example. And we also could show that we can determine alignment of stems to our mixes. So if we shift the stem where we know, okay, now it fits perfectly, and then we shift it slightly, we see that the cosine distance, cosine similarity decreases the further we shift the stem. So this makes it possible also to align, which is nice if it's a desired property of your model. And and an example of of equivariance. Using equivariance objective is PESTO, pitch estimation model, where we also put in two versions of the same signal. In this case, we crop it randomly. Basically means we pitch shift the signal, and we have so two pitch shifted versions of each other in our inputs. And here the constraint is not that we want to bring the latents close in space, but we want to basically impose a translation equivariant objective. Basically it means we know how far we shifted our input, and we then just force the model in the output predictions to shift the output prediction the same way. And so this is in that case, it's just a pitch estimation algorithm that comes out of it. And we also put some augmentations on it, like we noise the data a little bit and stuff, so that the model becomes more robust. And that's this worked extremely well. You know, you don't need any labeled data. You can just throw at it whatever data set you have, and we could show that, okay, the model is much smaller than the best performing model before. This was a CREP, I guess. So it's, I think, 800 times smaller, and it performs similarly well. And it also performs better to out of distribution data, so data that it hasn't seen during training. So it's a very lightweight, simple idea. But yeah, it's a self-supervised learning idea that also has shown to work pretty well. And yeah, and now we go to the more common autoencoder realm, let's say. Usually in an auto, yeah, so music to latent, it's an interesting model from different perspectives. First, it has a stochastic decoder. So we just basically have this symmetric encoder-decoder architecture like we know from autoencoders anyway. But then we perform this, or we connect the decoder layers to a consistency model unit. And consistency model is like a diffusion model, but it can generate data in one step. So at inference time, you just input noise into the consistency model and you condition it on some latent representations, and it outputs directly a signal. And again, here we use the real and imaginary coefficients. So basically we use the complex valued SDFT. And the advantage also is that compared to other autoencoders nowadays, modern autoencoders of audio, they use usually a lot of, or you need to use a lot of different losses. So you need, of course, a multi-scale SDFT loss. Often, or always actually, they also use some adversarial loss on the output in order to make the model work well. And if you have a VQ VAE in the bottleneck, if you want to discretize your data, you have again losses, commitment losses and stuff like this. But the music to latent works only with one loss, and that's the normal MSE loss on the output, which is actually very like MSE loss of the consistency model, which is pretty elegant, I think. And this leads to very strong compression. I mean, we don't discretize the data, so we have continuous latent representations. And there, yeah, we have 11 hertz for, or 12 hertz for 48 kilohertz input. So we have basically 11 for 44, we have 11 vectors. So we have 11 vectors per second of size 64 only. And we can still generate or decode it into really high quality audio data. And yeah, so if we compare it to other continuous autoencoders, continuous space autoencoders, we perform pretty well there. But also the Descript audio codec is kind of state of the art nowadays. If we compare the FAD of CLAP and FAD, we actually get very competitive results. If we compare the SI-SDR, like metrics that are dependent on phase and on where we actually need to reconstruct exactly the audio again, it doesn't look so good, but that's not a problem, I would argue, because what we care about is a very close reconstruction to the original signal, and that it sounds good to our ears as well. And so if you have a generative decoder, of course you cannot expect the same signal in your output than in your input, but in many cases this doesn't actually matter. And what was very interesting also to see is that these representations are very nice for downstream tasks. So they even outperform self-supervised learning approaches that are actually tailored to do well on downstream tasks, especially when it comes to pitch identification. Yeah, so I would actually argue if you perform any task on audio nowadays with any MIR task, you actually don't need to use the raw signal anymore. You just use these representations. You have a much more compact, low-dimensional representation of your audio. And then you perform whatever task you want on top of these representations. And I think, yeah, and if you can even reconstruct it again. But generally, for audio analysis tasks, I would just say just use those representations, and you have a pre-digested version of your signal for your model, whatever it is. How much time do I have? Cool. All right. So very quickly, audio analysis, audio synthesis. It shouldn't be the main focus of this talk, but I wanted to quickly mention it. So you might ask yourself why I mentioned drum gun in this talk, because it's really already a pretty old model, 2020, but it was an interesting model. Why I wanted to mention it is that we also have a web application now. It's also free to use, and everyone can just go there. Yeah, you can generate your set of drum samples. You can download it as WAV files. Just wanted to say this is online now, and yeah, I'm really happy that we can now provide this to the public. So next, differiff. Probably you've heard this already, because it was basically presented in the ISME conference just 2 months ago in San Francisco. But what's interesting is that here we actually combine all the things that I was talking about, all the concepts, to some degree. So we have first our music to latent encoder, where we encode a music context. Did I show you? Okay. Every one of you knows? Okay. I think probably I still should mention, okay, it's a stem generator. So what it does is you input a mix, and it generates you one instrument that fits the mix. And you can control it by either inputting an audio reference, so an audio file of a single instrument, and it will try to emulate this timbre and playing style. Or you can input the text prompt, and basically specifying the instrument that should play along to your mix. And so we encode the music context, and we encode also the audio reference or text prompt into a CLEP model. CLEP is a joint embedding space model for audio and text. So it doesn't matter if you input audio or text, it pretty much ends up in a similar position in space. And we condition our model on these CLEP representations, which is basically just a single vector. And so this is an example of self-supervised learning, joint embedding space. Here we have an example of our music to latent, because we use music to latent, obviously. And we generate also in the compressed space, so it's a latent diffusion model. So we generate the accompaniment instrument, the stem, in a compressed form, and then we decode again. And as a low-level representation, yeah, we use complex valued STFTs in our input and output, because, yeah, I'm convinced that's the best representation to use for generation. Yeah, and I did a bit of music with it the other day. Just wanted to, I picked 2 examples that I liked. So this is now without any additional stems. That's the input. Can you turn this up a bit? Can you turn this up a bit? Okay, so that was the input to the model, and then I just generated, asked the differiff to generate bass, drums, and voice to it. Okay, and the other thing is just to show that it works for different genres. We have this hip hop, if it works.
Hands up, wave me to the sky. Crowd lifts me, feels like I'm alive. Everybody hands up, wave me to the sky. Crowd lifts me, feels like I'm alive.
And here with edited stems.
Hands up, wave me to the sky. Crowd lifts me, feels like I'm alive. Everybody hands up, wave me to the sky. Crowd lifts me, feels like I'm alive.
Papa check the hate off there. Papa check the hate off there. Papa check the hate off there. Papa check the hate off there.
I mean, it's a bit unconventional, but somehow I like it a lot. I mean, I picked this because, yeah, it is very complex, and of course, it has not a strong signal as an input because it's really just voice. So the drums are free to do crazy stuff, but yeah, as an artistic output, I think it was very interesting. So last slide. Continuous autoregressive models. So we know if we want to do autoregressive generation, we first have to discretize our data. It's just simply how it works to predict from an autoregressive model. We need to do cross entropy. We need to have a distribution over our future tokens. So it's actually not possible to generate a sequence of continuous vectors. And so there were some works this year and maybe last year already on maybe making these continuous autoregressive models work. And in the end, we ended up with, because the main problem is, even if you have, like, so the basic idea is you have an autoregressive model like you use for current large language models and so on. And then you just condition a very small diffusion model on this past context, and then you generate just one vector at every time step with a diffusion model. So that's a very easy task to generate one vector. But the point is that at inference time, you actually, you're not precise enough, so you add up an error. So over several steps, you basically just wander off, and you accumulate an error at inference time. So this is the main challenge to solve. And some works, they used masking and iteratively sampling in order to solve this problem, but it wasn't really possible to perform this in a purely autoregressive way, just doing one step after the other. And this again work of Marco Passini. Is he here meanwhile? No. Okay, but that's work he just, basically he's not here because he comes back from the NeurIPS conference where he presented this paper. And the idea here is that during training, we just add some random noise to every of the previous vectors to just make the model robust and tell the model, okay, you shouldn't focus too much on the details, but rather on the trend. So we add some random noise with different amplitudes. And then at inference time, we also add a little bit of noise. And that's all, that's the idea, and this makes the model robust and not accumulate errors at inference time. So here are some examples. We just trained it on single instruments again, so don't listen so much on what they play, but just about they are consistent over 20 seconds, and the audio quality is not too bad, let's say. This also works for bass, of course. Yeah, so we showed it for different instruments, and we also compared it to other autoregressive models, and actually we could improve on the state of the art, which is cool. And so I think these continuous autoregressive models can be very interesting for real-time applications, because if we do, this is again using music to latent representations with very low number of vectors per time step. And so also the autoregressive model has the context is pretty short. So if we go for 10 seconds, we only have 100 vectors to deal with. And so I think, and it's causal. So I think this could be a nice model for real-time applications. And yeah, and a more effective way to use autoregressive models actually for audio. All right. So that's what we looked at today, low-level representations. If we learn them, we can do interesting stuff with it, and we have not an overcomplete dictionary, but we just learn what we need to learn. For generation, yeah, as I said, complex STFT is, I think, the best representation, at least is my choice. High-level representation learning, self-supervised learning, we can learn compatibilities like stem compatibility or drum sample compatibility, not only learning about the signal itself, but also about which signals, especially music that's interesting, what fits well to each other, to learn such things. And I presented the music to latent audio codec. And neural audio synthesis, yeah, we looked at latent diffusion on the example of diff-riff, stem generation. And we looked at continuous autoregressive models. Okay, thank you very much.